Hello, this is the explanation of yesterday's seminar. So here is the first question. It was about two. So the first part was calculating the mean time to failures in hours, and our failure rate was in hour. So in order to calculate the mean time to failure, we divide 1 to our failure rate, and for the first component it's 1 million hours, and for the second component it is around 10,000. In the next section, we were asked to calculate the reliability for 1 year. Here we are dealing with year as time unit, so we cannot use the previous failure rates in hours because then it will calculate our reliability in hours. So first we need to change our failure rates from hours to year, and for doing so we multiply the failure rate to the number of hours per year, so it will give us the failure rate per hour. And then for reliability, we can calculate it based on the failure rate that we have just calculated. And this is our reliability. And you can see the reliability of part A is much higher than the reliability of part B. It can work up to 1 million hours. The mean time to failure is 1 million hours, so it's a very reliable component. The next part was about calculating the unavailability when we know that mean downtime is 10 hours. This is the time that our system is working and it's operational, and this is the time that our system is down for maintenance and repair. So if we want to calculate the unavailability, we need the data about this percentage of the time to the whole life, to the whole cycle that we have. So in order to calculate it, we can directly calculate it by this formula, or we can use the availability function. But if we put the mean time to failure for each component into this formula, we come up to these numbers, and we can see that the unavailability rate for component B is higher because it has a higher failure rate and a lower mean time to failure. So this component is breakdown more often. The last part of the question A was about calculating the reliability of working for 3 years when we know that our system has been working for 1 year. And based on what I explained during the seminar, this is how we calculate it. We know this is the conditional probability that we use because we know that it has been working for 1 year, and the exponential distribution, they do not have any memory. So when it has been working for 1 year, if we want to know what's the probability of working at the 3rd year, we just need to calculate the reliability for more 2 years. So this is the number and the final result for the reliability of our system to be working at the 3rd year. The next question was about parallel and series system, and we need to calculate the reliability of the whole system. We had this reliability and this component from the first question, so this is A and B. They are similar to the component that we had in the previous question, and now this is how they have been designed to work together in a system. And we need to calculate the reliability of the system in 3 years. So what we need to do, this is my suggestion. When you want to calculate the reliability of the whole system, try to divide it into subsystems. In this exercise, we first calculate the probability of the first of the, this part, number 1. Then we calculate number 2. So we have the reliability of the first, line of the parallel system. Then we go to number 3 and number 4. It would be more easy and you may not make mistakes if we want to write a big calculation and formula, it's more the probability of making a mistake is higher. So here is the formula. I wrote them for each part that we divided, and then this is the total reliability of our system. And you can check your calculation to see whether you have done it correctly or not. I wanted to show you something interesting. This is the reliability plot of the component A. This is component A. This is component B. And this is the reliability of our system. So if you see, we have a very reliable component. That's component A. And we have an unreliable component that we try to somehow compensate the low reliability rate by making it parallel. But you can see that until, for example, 10 months, or maybe we can say here 1 year, it's almost okay to use that system and that design. But after 1 year, the reliability decreased drastically. So it shows us that this is not a very good design. And as I told you during the lecture day, you can see this is the exponential distribution. You can see it's a very perfect exponential distribution. We have it for component A also. But for the whole system, you can see it is not perfectly does not perfectly fit the exponential distribution. So this is what we deal in reality when we are working with reliability functions. And we had another part that we try to improve the reliability of our system hypothetically, and we added component C to our design. This is our component has this failure hours rate, and it has broke down in these hours. I changed the primary data that I gave you during the seminar, so I multiply them by 10 because otherwise the reliability would be around 0. So please check these data. They are a little bit different. Just they are multiplied by 10 from the data that you have. So if you want to calculate the reliability of the whole system, we need to calculate the reliability of the component C. And we know that it follows a Weibull distribution. So we need to use the Weibull distribution parameter estimation. There are lots of different ways to estimate the Weibull parameters, and one of them is the Weibull paper that we will work during the class, this class. So first we sort the reliability, the failure time. You can see we sort them from lowest to highest. Then we have this J number. This would be the rank of each failure time, and we calculate this number for each failure time. So in order to estimate the parameters, we use Weibull paper. For plotting, we need to scale our data because they were around 25,000 to 75,000. And then we need to scale them so that we can find the data points here. Here is the 20.5, and then we will, and the other data, we put them here. Then we fit a line more close to the data points that we found, and this line will help us to estimate the distribution parameters. So in order to find the alpha, we draw a line from the 0 point to the line we have from here, and then come straight down, and here is the approximation of the alpha parameters. And when we want to find the beta parameters, then we shift the line to this point. No, it's not completely at the point, but and then you can find the data, the beta from here. So based on this line and this Weibull paper, we can estimate the alpha and beta parameters. So by that Weibull paper, we come up to this parameter, 84,000 for alpha and 2.5 for beta. And if we calculate the reliability for 3 years from the formula that we have, we come up to 80% reliability for 3 years. Like the previous example, then we divide if we want to calculate the reliability of our system, we have the reliability for these parts. So we will divide it to two separate subsystem. We first calculate the one and then go to the second. So the reliability of the first part is the parallel system, so it would be 99%. So you can see that the reliability is quite high. And if we calculate the reliability of the whole system, we see that it doesn't really change the reliability, and it stay the same. So it's a good design because it doesn't affect our reliability, our previous reliability. But if you want to somehow analyze it, you need to see how much cost do you spend for adding new components, and when it doesn't improve the reliability, does it worth it or not? So there would be lots of analysis about how it will really improve our design or not.